Welcome to the image processing portion of the micro-CT video. I am Michelle Ploux. CT scans produce large data files that can be up to 20 to 30 gigabytes in size. The first type of data that the micro-CT produces is the raw projection data. This data is a series of thousands of X-ray images taken around a single rotation of the specimen. Shown here is a video of thousands of X-ray projections for a honeybee scanned in the micro-CT. A computer then uses the projection data to reconstruct a final set of images that shows the three-dimensional detail of the specimen. The reconstruction data comes in the form of a stack of TIFF or DICOM images that depict the sequential cross-sectional structures of a sample from top to bottom. This stack of images is also called a Z-stack. The Z-stack of the bee shows not only the external, but also the internal anatomy of each cross-section. The Z-stacks can be used to virtually inspect, measure, and illustrate the overall anatomy of the specimen. The Z-stacks are loaded into software where they can be visualized in 3D, and specific ranges of gray values, which represent different densities or materials, can be labeled. These labels can then be turned into 3D models and animation. Here, a 3D surface is made of the exterior of the bee. If you were to digitally slice through this model, you would still find all the internal anatomy depicted in the Z-stack. 3D models can then be sent to a 3D printer to create a physical representation of the original sample. 3D printed models can be scaled up for easy examination of the specimen and put on display without worry of damage to the original. Because of the non-destructive nature of the micro-CT and its ability to visualize structures that are otherwise difficult or impossible to see, it has become a popular tool in many fields of research. You've already seen some examples of a USB and its internal circuitry being examined, of animal muscles and skeletons being scanned, and of fossils being digitized. The micro-CT can be used to illuminate delicate structures like the intrusions of roots in soil. The less dense materials, like the roots cutting through the core, are colored in blue, while the more dense pebbles and dirt are in oranges and reds. The roots can also be isolated and studied as if they were suspended in air. The above examples are only a small slice of the types of research that use the micro-CT. Some other interesting applications include work on mummies, paintings, archaeological artifacts, and much, much more. Ariana will now show you how these different kinds of CT data are created for fossil samples.
I used the micro-CT scanner to study these fossils because they were very small animals. Some of them were only the size of a mouse. Small animals have very small bones that are difficult to describe and measure using just the naked eye. They are also more difficult to handle and easy to lose track of, which can be extremely stressful because fossils are irreplaceable. Using micro-CT scanner lets us make a digital copy of the fossil so that we can virtually manipulate it. We can blow it up to any size on the computer so that anatomical features can be more easily seen and measured, and the CT scans help us preserve and archive these fossils digitally in case a fossil is accidentally lost or broken in the future. After the specimen has been scanned and reconstructed, I use two programs to process and visualize the data. The first program I use is a free program called ImageJ, where I crop the stack of scanned images to make the dataset smaller and more manageable, and so that I can separate out and better keep track of many fossils that I have included in the single scan. I do this by opening the TIFF stack in ImageJ, selecting the area of interest, and selecting Crop. I then save this new image stack with the specimen number and the file name. Next, I produce virtually reconstructed 3D surfaces of the fossils in the 3D visualization program Aviso. In Aviso, I open up the TIFF stacks of the images I just cropped in ImageJ. I select the volume of interest using a specific tool in the program and do the smoothing steps to decrease the noisiness of the 3D model and produce high-resolution surfaces for looking at on the computer or for 3D printing. Ultimately, I'll upload these scans to an online repository for such data, morphosource.org, so that other researchers can look at the same specimens without ever having to pull the fragile original out of the museum drawer.